Okay, so hopefully a lot of this is a review except for the math. So we're going to talk about SID today, and we are going to talk about changing SID as it relates to magnification, changing SID as it relates to radiation levels or intensity. And then speaking of intensity, we are going to be able to figure out what your new intensity is. So you have to be given the first intensity. You have to know how much radiation there is. And then you should be able to figure out how much radiation you have when you change your SID. Either bring it closer to the image receptor, which in that case, right, it should go up because you're closer, or the opposite direction. And so that we'll get into inverse square law. But even more importantly, in my mind, because how often in clinic did you try to figure out how much radiation there was yesterday? Probably not at all. But you may have seen technologists think about what their exposure should be if their distance was different from what they might usually use. Anyone do any cases on a stretcher? Yeah. Right? Cases on a stretcher require them to measure usually. No? Just
they
like
eyed it.
They eyeballed it?
Yeah.
Well, okay, so you're going to see, I'm skipping around a little bit, but you're going to see there's sort of a rule of thumb in that if you have an exposure that you know works at a certain SID, unless that SID changes by 15%, which turns out, if it's 72 inches, that would be like almost a foot. So unless you're off by 12, 13 inches when you're trying to do something at 72, you leave your technique the same. So if you're doing something at 40, you would have to be off by 6, 7 inches before you really need to change your technique. So you can eyeball something. If they've measured, and one of the things you'll start to learn is your own body. You'll know where your hands are. And once you've measured enough times, you'll kind of probably get to the point where you're within inches of where you always are and need to be. So trust me, there'll be times when you say something that a tech did and I'll frown and not be too upset. But sometimes when they eyeball things, they're probably pretty accurate. They've been doing it enough times and they're used to working in certain rooms and certain stretchers, and the stretcher happens to come up to their waist. So it's hard to say. So in terms of our intro here, we'll turn the lights off a little bit so it's a little nicer in here. For the most part, we're going to be doing things at either 40 inches or 72. And everything should lock into place unless you're on a portable exam where nothing locks into place and you just have to use your tape measure, or you're doing work in a stretcher, right? Then the SID is kind of hard to figure out. I mean, unless you eyeball it or actually measure. So, yes, the illustrious tape measure. So when it comes to spatial resolution or sharpness, there should be a review, right? When we have a longer SID, you can see here that our ultimate penumbra is much less than the penumbra on the left side with the shorter SID, right? So shorter SID has more penumbra, that means more blur. Remember that word, penumbra? And more blur means resolution goes down, right? Sharpness, spatial resolution goes down. These are things, again, that will happen more often when patients are on stretchers or in wheelchairs, and you're trying to do things that are not on the table. Whenever possible, I try to get people on the table. So we try, whenever possible, to keep our OID down, but on this slide, for sure, we try to keep our SID up. Now, SID should be up for two reasons. One is sharpness, right? So penumbra goes down, but also the effect on magnification, right? So in particular, when you're doing a portable exam, we know that magnification goes down when SID goes up. That can only help you on a portable exam, right? That'll help, hopefully, prevent you from cutting anatomy. So when you have a patient that's semi-erect, right, in the stretcher and you sit them up, right, you want to bring that tube back as far as you can. And if you're doing an AP supine chest, you want to bring the tube up as high as you can. You're not going to get 72 because you just can't reach it. You might get somewhere around 48, 50 inches. You know, maybe the bed goes down or the stretcher goes down. You can kind of try to extend things at both ends. But that's what you should do because you will minimize the anatomy and you'll have less chance of cutting on a chest x-ray. Sometimes no matter what you do, you cut. And that's just the way it is sometimes. All right. Now, of course, and we'll address it in a few minutes, depending on how much you change your SID, you're going to have to change your exposure. Right? You can't use the same mass that works at 40 when you switch to 72 or vice versa. Right? But we'll get to that in a second. So speaking of magnification, you also, another reason to keep your SID higher, which would be to minimize things, but also you get better resolution, right? Your sharpness increases because your penumbra goes down here compared to here at the lower or less SID. Can I hide that maybe? So far, so good, right? And we did this in the lab last year. It's not huge. You don't see a big difference in magnification if you only change things by a few inches. Certainly in SID, you don't see much, right? When we did this in the lab, we did exactly what they did. They switched from 40 inches SID all the way to 20 inches to get this thing to magnify. Generally speaking, even if you're eyeballing things, I don't think you're going to make like a 50% mistake, you know, where you're off half of what you thought you were going to do. But it's useful. The other thing I think maybe techs have gotten a little bit complacent is techniques in general now have a much wider latitude because of the digital processing. You know, one day we should do like a special lab where we just try to do stuff with film. You have to be dead on with film, pretty much. A little bit more kV or a little bit more mass, and it represents itself as being dark. And you can't fix it. It's a piece of film. You know, you're done. If you use not enough kV or a little bit less mass than you should have used, it's going to be light. And that's still a problem with digital imaging. Remember, light ends up really being noise, which we'll see in a few minutes. And the computers are not good at fixing noise. They're better at fixing overexposures, which is good for the image, but bad for the patient. So when it comes to exposure, I know you've gone over some of these principles in protection. And you may have heard of the inverse square law. When you double the SID, exposure is going to go up or down? You tell me. It's going to go way down, right? Because you're much further away. What is actually happening is photons just don't make it to the image receptor. They just die on the way there. Or they kind of go off to the sides and never hit, right? The calculation that we're about to go over is based on what's known as the inverse square law. And if you have a question where the SID doubles or the SID is cut in half, that's easy, right? Because you shouldn't have to do the math, right? Because you can do it in your head. If the SID is cut in half, for example, the radiation we know goes up. how much up? It quadruples 4 times. If you had like 10 millisieverts, now you have 40 millisieverts. The equation will come in when they tell you how much radiation you start with. They want to know how much you end up with when you change your SID. And it's easy to figure out, again, if you half the SID or double the SID. But what if you go from 40 inches to 36 inches? That one, if you could do it in your head, you should be in a different major, right? But that's where the formula really comes into play. Also, the light field changes in the same way, right? Without changing the collimator, if you double your distance, the light field expands by 4 times. So I probably will get rid of this slide because it talks about film, and I no longer really talk about film. But I did mention it a few minutes ago, right? Our visual aspect of whether the patient had too much radiation or too little is gone, right? We don't have a visual cue because in the past, right, if you lowered the SID, not only would the exposure go up, but the density, the blackening on the film, would show up as it being a darker image. It was pretty obvious that you used too much. Now what do we have to represent our radiation exposure? The EI, right? We only have our exposure indicator to do that. And it's tough now because the digital processing fixes the images. So all you really have is that number, because the image might look good, and you might get written up if you start using a technique over and over and over again, leading to multiple overexposures to patients, and because you basically didn't look at the EI, you just looked and made sure, like, you know, all the anatomy is there. So you got to look at that exposure indicator. Right? Have you guys seen it at the hospital? Find where it is. Well, it's not where. Usually, you don't see it. Well, it depends if you're using CR or DR, right? If you're using DR, it shows up on the screen, right there with your image. If you're doing CR, then obviously it's not going to show up at the exposure. It's going to show up wherever the processing unit is, right, when it comes up. But technologists should be looking for that, or maybe it's color coded, right? Sometimes it's like a yellow, a red, and a green to kind of show you the range that you're in. The irony, I suspect, is exposures have crept up, even though digital imaging allows you to use less exposure than film, technically. But because of the fixability, just made that one up, of the processor, people end up exposing higher than they used to, even with film. The idea was digital imaging would lower radiation dose to the patient, and that's true if used properly. So when you don't use enough exposure, that's the only time, besides the exposure indicator being off, where you might actually see it represented in the image as noise or quantum models, so it shows up as this grainy appearance. And again, when it comes to SID, I mentioned it earlier, so I'll just very briefly say it again since we're on this slide. Unless your SID changes by about 15%, then you shouldn't need to actually change your technique. Right? 2 inches off of your SID is not going to change anything. I mean, intensity will go up or down ever so slightly. So when I say it doesn't change anything, that's not completely true, right? The intensity changes a little bit, but not enough to be outside of the parameters of the processing ability of the digital image. And the magnification will also be pretty low too. So got to know when to change things and when not to change things. This would be terrible. That's a repeat. Big time. I mean, everything's there, but no good. So the inverse square law. Okay, so before you start writing things down, I don't like this formula. I use a different formula. I think my formula is easier. I'm like one of those parents when they come and their kid comes home and like they do division some completely different way than when I learned it, like long division. And they do stuff on the opposite side and like they multiply using like some square method and they put things outside the square. Anyway, so I have my own calculation that I'm happy with. You're welcome to use this. It's math. I don't care how you get the correct answer. So that said, I'll write it over here. I use intensity 1 over intensity 2 equals distance 2 over distance 1. Yeah, don't forget the square. You guys know me. If you forget the square, you'll get an answer. It'll be the wrong answer on the test. You're welcome to use this. It's pretty much the same. They use old versus new. I use 1 versus 2. Okay. The reason why we know it's inverse square law is two things. One is 1, 2, 2, 1. Right? The other is the I. Okay? We're dealing with radiation, we're dealing with intensity. If you see a question that's like, what's my new mass? That's the other formula that we're going to talk about in a couple minutes. Right? So we'll kind of look here, because it's kind of messy now. Look here. This on the left side, I might just have to get rid of. This is just proving that the inverse square works, and is showing you that your radiation changes and is essentially a quarter of the radiation when your SID is chopped in half. That's not the kind of problem you're going to get. You're going to get a problem more similar to what's on the right side. So let's take a look at this one. This one says, at an SID of 80 cm, I get an exposure for whatever technique that I used that gives me, if I were to have used a dosimeter, 50 MR. So at 80 SID, I get 50 MR. Now, I want to know what that new MR is going to be, that new exposure, if I now go to 140 cm. So first of all, you should think, does the radiation go up or down? That should be your first thought, without even doing the calculation yet. Right? If I'm going from 80 to 140, my radiation is going to go down, right? Because my SID is much further. Right? If I went from 80 to 160, then I should know that it will quarter at that point, because it's exact. And this is in between them. So unless you're really good, and you should change majors, like I said before, you have to plug it in to do the formula. So in this case, right, we're going to take I1 over I2 equals D2 over D1, so I'm going to kind of write it like this. You guys can do it however you want, again. Right? So our first SID is 80, so that's this one, right? 80. And that gives us an intensity of 50 MR, that's this one. 50. You don't have to write the units until the end. And we're now moving to 140. That's my second one, that's this one, right? And we want to know what the new intensity is. So realize I'm basically done, right? Unless I really make a mistake on my math now, right? Plugging everything in the right spot is super duper important, right? You plug something in the wrong place, or you forget to do the square and just do straight division or whatever. As mentioned, not to be evil, you'll get an answer on the test. It'll be one of the wrong choices, right? I don't just put any random number. I put the likely types of mistakes. I'm not the only one that does this. They probably do that in math all the time. So don't bother, reducing or anything. You're going to have a calculator to do this. Use big numbers. It doesn't matter. So we have 50 over x is equal to 140 times 140. What is that? 19,600. 19,600. And then 80 times 80 is 6,400, right? Okay. Now I cross multiply. I get 6,400. Oops, sorry. I get.
Yes, I'm 50.
Well, I like to do it this way. I get 19600x is equal to whatever 50 times that is, which is what? 320, right? Then I divide so that I can get x alone, right? And I get x equals whatever 320,000 divided by 19,600 is, and I happen to have the answer here, 16.3. 16.3 MR, right, million. Okay. Don't leave the unit off because you might see the same answer there twice, one with it, one without it. Choose the one with the unit, or choose the one with the correct unit too. Not so bad, right? The book has a few more examples. If any of you guys have that handbook from last year that you might have gotten, there's more examples in there on inverse square law. And if you want someone else to show you how to do inverse square law, I found a YouTube video of someone else doing inverse square law, but we're not going to watch it now. So the compensating technique, or otherwise known as the square law, is the one that I think is more realistic, right? Because this is where the distance changes, which we now know, and we've known actually all along, is that will cause the intensity to change. But that change in intensity should require you to compensate your exposure, change your technique. So the direct square law deals with mass, right? Because if your tube moves further away, intensity goes down, which means you need more mass, right? So one of the things you do with these questions too is also figure out whether the mass is going to go up or down. You might be able to, get rid of a choice that way, just pretty quickly. Yes.
So the mass, will we have to compensate the kV as well?
No. No. So the direct square law is with mass. Funny you mention that because the question that is on the next slide has kV in the question and it's irrelevant. You'll see in a second. So I feel that this makes more sense to use clinically because, we don't usually think about whether the radiation is going up or down. And we don't talk to anyone really about it. But we do have to recognize whether intensity is going to change and then how to actually change our exposure. So this is the calculation that, if you're going to use one, this is the one you might actually use. Even if you're using it in your head, kind of. So again, I don't really like their formula. They use O's and N's or whatever it is for new and old. I use 1s and 2s. So when I write this down, maybe I have a spot over here. I use MAS 1, MAS 2 equals D1, D2 squared. So first of all, there's no I's in here. There's no intensity. We're dealing with mass, we're not dealing with radiation, even though it's kind of And notice it's direct square law because it goes 1, 2, 1, 2, where the other one was 1, 2, 2, 1. So two formulas, you have to know which one to use depending on what the problem is, and then you have to write it correctly, right? So if you mix any of these up, or if you plug in things in the wrong place, that's how you get the answer incorrect, right? So, now if you know that you need to, double the exposure, you can use 15% rule for kV. But if the problem is related to what your new mass is, you have to use the direct square formula. So let's do one. Here's one. Maybe I'll use this part. And it goes on. So let's take a look at this one. Using an SID of 40, a radiographic technique of 72 kV and 10 mass gives us a good exposure. The whole idea is if your initial exposure doesn't work well, then changing it to a new exposure is probably not going to work either, even if you follow the rules of the formula. That's why they're like results in a satisfactory exposure. What happens if your SID is now changed to 96? What should your new mass be so that you end up getting the same exposure, which means your exposure indicator should end up being pretty much the same? So let's do it. Again, MAS1, MAS2 equals D1, D2 squared. So, using an SID of 40, that's my first distance. A radiographic technique is 72 kV. kV? No. Irrelevant. So you think I'm the only evil person that puts information into questions that you don't really need? No, I'm not. Okay, so we don't need that because it doesn't apply. Okay, and we used 40 inches SID at 10 mass. That's our first mass. And then we switched to 96 inches. What is our new mass going to be? So again, first thing you do is ask yourself, should the number be going up or number be going down? So what's happened? We're going from 40 to 96. That's much more SID. So it's a two-part thing, right? Much more SID means the intensity goes down, which means we need more mass. So our mass number should be higher. Hopefully you eliminate a choice right there. So once you've gotten to this part, it should be easy. You just got to do the squaring stuff first. Right? That's the whole PEMDAS rule. Right? You guys remember that from somewhere? Okay, so 10 over x equals, can you reduce the fraction? Feel free to do any of those things if you want, but you have a calculator, just use big numbers so that you don't make a mistake somewhere. Right? So 40 times 40 is 1600. 96 times 96 is, I don't know. 92, what is it? 92, 160?
9,216.
9,216.
Okay, so now I cross multiply. We get 1600x, right? And 92160, right, times 10. Now we want to isolate x, so we divide by 1600, and we get x equals whatever that is. 57.6 mass. Can you get 57.6 mass? Probably not. So on the test, it might say 58, right? It might be rounded off. right? And the other numbers will be way off, right? They won't be like so close that you won't be able to pick the correct choice. Terrible? Not so bad. Remember though, if the SID either doubles or halves, then you can do the math in your head, right? Because either things will quarter or quadruple, right? It's when you have a question that says the SID changes and it only changes by like 6 inches, then you have to plug in the numbers. The book has this rule of thumb stuff. I don't really like it. I guess it's helpful because I will have to go out and meet the technologist. If you ever come to me and tell me someone was caught doing inverse square law on the back of a napkin or direct square law to figure out what their new technique is, what do? They just know to go up or down based on their distance. And they've been doing it enough that, similar to eyeballing it, they know that they can guesstimate, how many steps in mass to go up or down. The way some of you probably saw me yesterday messing with the portable machine, right? And still managing somehow, yay me, to get into range on subsequent exposures, on many of them, right? But technically, you could do this, right? The problem is the patient. You don't always know what to use in the first place, right? So a lot of these assumptions are that you had a technique that worked at a certain distance. Now it changes. Now you know exactly how to change that technique, but it had to work in the first place. So I'm not going to test you on these. You don't have to memorize this. It's not bad to kind of like look at and get an idea, because generally speaking, things are not going to change by half or double, right? You're going to try to do something at 40 inches, but now because they're in a stretcher and the way the room is, you might only be able to get, I don't know, let's say 31 inches. It's never going to be so bad that you're going to be forced to use half of what you would originally use. And I can't imagine, 20 inches. Do you know how far away that is from the patient? That's like right on top of them. Okay? So that's probably not really going to happen. So I think that's pretty much it. So I will leave it here. But what I want to hear from you before